So let's just jump right in. Imagine this, a volcano erupts and you've got to evacuate 50,000 people. Now, what if that volcano erupts again, but with even more force, and you have to move all those people a second time, and then a third? This isn't some disaster movie plot. It's exactly what happened in 2010 at Indonesia's Mount Merapi, and it blew the lid off a huge challenge in disaster planning.
And what's truly, frankly, terrifying about this whole situation is captured in this one quote from the official report. I mean, just picture the chaos. The official plans are toast, and thousands of people are just running. They don't have a destination. They're just trying to outrun the volcano's fury. That's the human cost right there when a crisis completely outgrows the plan. And this timeline? Wow, it just shows how fast everything went sideways. On October 26th, the first safe zone was set at 10 kilometers. Okay, just over a week later, boom, a bigger eruption pushes it to 15. Then, only 2 days after that, a massive explosion forces them to extend the danger zone to a full 20 kilometers. The threat was literally getting bigger by the day. 3. That's how many times people were forced to pack up their lives and move in about 10 days. Can you imagine? Each time, they thought they were getting to safety, and each time, the volcano proved them wrong. This wasn't just some inconvenience. It was a total collapse of the emergency strategy they had in place. And here's the kicker. The original disaster plan, it relied on permanent, pre-picked shelters. But as that safe zone kept expanding from 10 to 15 to 20 kilometers, many of those safe shelters ended up inside the new danger zones. The plan just couldn't keep up with a crisis that was getting more powerful. It became obsolete in real time.
All right, but the problem gets even trickier because it's not just about the volcano. You have to factor in human behavior. See, it's not just about finding a safe spot on a map. It's about getting people to actually go there. And this brings us to the challenge of what's called dynamic evacuation.
So what does that even mean? Well, think about it. If you live near a volcano, you probably don't want to pack up and move 20 kilometers away at the very first rumble. You want to stay close to your home, your farm, your animals. So people tend to move in stages, just far enough away to feel safe for the moment, hoping they can go back soon. You can't just order everyone to leave. You have to plan for how people actually behave. And this map really drives that point home. We're looking at the Slayman Regency, the whole area around Mount Merapi. For the people here, this land is, well, it's everything. It's where they make their living, where their families have been for generations. Asking them to just get up and leave for good isn't a first step. It's the absolute last resort.
So you have this incredibly complex problem, an unpredictable volcano on one hand, and a population that moves in stages on the other. How on earth do you create a plan that actually works? Well, the answer, it turns out, is in a high-tech, data-driven approach that can adapt on the fly. Researchers broke it down into this really smart 4-step game plan. First, you figure out what actually makes a good temporary shelter. Second, you find all the possible places that could work. Schools, government buildings, community halls. Third, you bring in the experts to decide which of those criteria matter most. And finally, you use a system to crunch all that data and give every single location a score. Now, the engine behind all of this is a technology called a Geographic Information System, or GIS. And the easiest way to wrap your head around it is to think of it like a super-powered smart map. It's like Google Maps on steroids. It can take tons of different layers of information, things like roads, rivers, hazard zones, and see how they all connect and overlap in a single place. And the goal for using this GIS model was super specific. Find the best temporary shelters, not permanent ones. And this is the most important part. Do it for each stage of an evacuation, whether the danger zone is 10, 15, or 20 kilometers wide. It's a model that's built to be flexible. So what exactly is the secret sauce in this model? What's on the checklist for a perfect temporary shelter? This is where all that data really starts to tell a story. Okay, this is really smart. The model splits all the criteria into 2 big buckets. On one side, you've got constraints. These are the absolute deal breakers. If a spot fails one of these, it's out, no questions asked. On the other side, you have factors. These are more like nice-to-haves that make a shelter better or worse. They're what's used to give a final score to all the places that passed the first test. And those deal breakers, they're all about immediate, non-negotiable safety. First, a shelter absolutely cannot be in a known hazard zone. These are areas that are always at high risk for lava or deadly gas flows. Second, it has to be outside whatever the current safety radius is for that specific eruption, plus an extra 1 kilometer buffer just to be extra safe. If a location is inside either of those lines, it's immediately disqualified, period. Okay, so for the spots that are still in the running, now we get to the scoring. This is where it gets really detailed. The model looks at things like, is it near a river that could flood with volcanic mud? How easy is it to get to? Is it close to a hospital or a market for supplies? Does it have power and clean water? And, is it actually big enough to hold people? Every single one of these adds or subtracts points from a location's final suitability score. All right, so we've got the rules and we've got the scoring system. Let's actually see how this GIS model puts all of that data to work to map out a path to safety. So here's how the smart map gets going. First, it takes a basic map of the region showing all the villages and roads, and it lays the permanent hazard zones right on top. These are the areas you see in red, orange, and yellow. They're always considered high risk, no matter what the volcano is doing on any given day. Now, here comes the cool dynamic part. Let's say officials declare a 15-kilometer safety radius. The model draws that circle on the map, and then, poof, it digitally erases every single possible location that falls inside that zone. What you're left with are only the places that meet that most basic safety rule. So, with all the obviously unsafe spots gone, the model can now focus on what's left. It's done with a simple pass-fail test, and now it can move on to the much more detailed job of scoring every single candidate location that's still on the map. And how does it score them? It uses a couple of really clever, well-established methods. First is something called the analytical hierarchy process, which is basically a fancy way of getting disaster experts to rank what's most important. They decide that being near a hospital is maybe more important than being near a market. Then, a formula called a weighted linear combination takes those expert rankings and calculates a final weighted suitability score for each and every spot. So the result would look something like this. You'd see that location A gets a really high score because it's easy to get to and it's close to a hospital. Location B, well, it's got tons of space, but it's far from a main road, so it gets a medium score. And location C is just too small and doesn't have good water, so it gets a low score. The model actually puts a number on how good each option really is. And the grand finale is this, a clear, simple map that doesn't just show you a bunch of safe locations, it actually ranks them from best to worst. Emergency planners can just look at this and instantly see their top 5 or top 10 best options, which lets them make incredibly fast, data-driven decisions when every single second matters. And what's so powerful about all of this is that this method isn't just for Mount Merapi. It's a blueprint. This whole approach, combining smart maps, expert opinions, and dynamic models, can be used for floods, for earthquakes, for hurricanes. It's a recipe for creating smarter, more flexible, and honestly more humane disaster plans that can save lives anywhere in the world. This whole thing proves we have the tools now to move way beyond those old, static, one-size-fits-all disaster plans. And it leaves us with a really big question to think about. As our technology gets more and more powerful, how else can we use data, not just to react to disasters, but to actually get ahead of them and protect our communities before the worst even happens?